Okay, let us start with one example. Okay, inside the pipe, okay, there is a valve, okay, initially closed, and what you do is you open the valve. So when the valve is open, your working fluid, which is R134E, can transfer from point 1 here to point 2. Okay. Given the properties of your working fluid, refrigerant 134E at point 1 and also at point 2. Okay. Find the amount of entropy generated during the expansion process if the process is operating under steady state conditions. So you are looking at this control volume. This is your system. Okay, you are not looking at the air outside your pipe. And here, amount of entropy generated, meaning that you are looking for S gen. Okay, but in this question, the mass flow rate is not given, so we are looking for S gen in the unit of kilojoule, kilogram, Kelvin. Okay, so that is the one that you need to find. To get started, we start with the entropy balance equation. Okay, this is the basic entropy balance equation. From there, we know that as in an entropy can be transferred by heat and mass, so we can expand this part to change of entropy due to the heat transfer plus with the change of entropy due to the mass transfer. Okay, refer back to our lecture notes. Okay, this is due to heat, entropy that is being transferred by heat, and this is entropy that is being transferred by mass. Then you plus with S gen equal to the change of entropy inside the system. In this case, the process happen under steady state, meaning that your change of entropy inside the system does not change with time. So what do you have there? Delta S over T is equal to 0. So your S gen is equal to MS plus or minus lah kan, because you move it there, Q over T. Oops, no T, no dot there. Okay, this one in the unit of kilojoule per Kelvin. Okay, do you have any entropy because of heat transfer? Of course no. How do you know that? Look at the diagram. It says that it's a well-insulated pipe, so no heat coming into your system or going out from your system. So this part becomes 0. You can cancel out. Okay, only the change of entropy due to the mass transfer. Okay, this delta MS there refer to MS from the inlet minus MS at the exit point. So in this case, you will have MS2 minus MS1. The mass flow rate or constant kan? So you will have S10 divided with the M equal to S2 minus S1. This will give you in the unit of kilojoule, kilogram, Kelvin. Okay, now we are done with the entropy balance equation. Try to find the delta S. Delta S. First thing that you have to do is identify your substance. Okay, in this case your substance is R134A, so it's a pure substance. Okay, if it's a pure substance, always go to property table. Okay, so we look at our property table to find our S2 and S1. Which table you should refer to? You have to find first. Make sure that you are looking at the R134A. Okay, R134A. Okay, is it A11, A12 or A13? Look at the given information there. It says that your T is 30 degrees Celsius and then your P is 700 kilopascal. Okay. In that case, we go to A12. Now, in A12, here, 700 kilopascal. Look at the saturated temperature. It's saturated, change the phase at 26 degrees Celsius, while your temperature is 30 degrees Celsius. So, your given T, which is 30 degrees Celsius, is larger than the T saturated 26. So what happened if you look back at your TS diagram? If the saturated temperature is as if the given temperature is larger than the T saturated, meaning that you are now at the superheated region. So we should go to A13. Okay, now look at A13. In A13, here, you have the 700 kilopascal and the given T is 30 degrees Celsius. So this is where you should get your reading for the S. Yeah, we're looking for S. Okay, so which one is our S? Here, 0.9313. That is our S. Okay, so our S1 equal to 0.9313 kilojoule per kilogram Kelvin. We do the same thing for S2. S2, we know that 0.2 it exists as saturated vapor and 60 kilopascal. Go back to our property table there. It's saturated vapor. Clearly, it's saturated vapor. And the given pressure is 60. Okay, so now we go to A12. Here, A12 at 60 kilopascal, your S, we take SG. Okay, not SF, not SFGY, because the sentence says that it leaves the valve in the form of saturated vapor. So your S2 is 0.96441. Okay. So coming back to our so your S2 here is equal to 0.96441 kilojoule kilogram Kelvin. So we can find the final answer as Gen. This is the amount of entropy being generated during the expansion process.